Will air in the system cause problems? ASHRAE says yes. If you get air in the system, you're going to get noise, you're going to lose stability of the system, you're going to lose heating and cooling ability. So noise comes from high velocity. You got air in train, it's going to be noisy. And it's going to, you can hear that little bubbles being pumped around the system per ASHRAE. So we definitely want to control the air. We definitely want to try to get the air out of the system if we can to avoid problems. Notice this particular situation, I've got a heating coil or a cooling coil that's air bound. And the pump's on. How do I know the pump's on? Because the supply main water column is higher than the return main water column. See the difference in the two? So we know the pump's on, but there's air up there, and the air is trapped. So we have no flow through the heating coil and or the cooling coil here. No flow means no heat. No flow means no cooling. That's bad, all because of air. So let's look at the point of no pressure change and what happens if we get air out in the closed system. Now, real quick at this slide, you've seen it before. We got an expansion tank. We got 12 panels pumping away from the expansion tank. We got great system pressure control. But look over to the right. What would happen if these little round football-shaped things are air bubbles out in the system? They're air-bound coils out in the system, just like the one I just showed you in a previous slide. How does the pump know which one is the boss? How does the pump know where the point of no pressure change is? We don't know what's going to happen. You start getting air out of the heating coils, the cooling coils, they might behave like an expansion tank. The pump's stupid. It doesn't know where you intended for the point of no pressure change to be. It's back at the expansion tank, but it doesn't know that if you put air bubbles out in your system. So that's really a bad thing to have happen. Here's a primary, secondary, variable volume system with a variable speed drive on it, a chill water system, great system. We put it in to be very efficient, lower that pump speed down, save all that energy, and we let air pockets get into the cooling coils. Look at that center cooling coil. It's got an air pocket at the top of it, okay? We got a two-way valve on it. What does that mean? Stop and think a little bit. An air pocket is going to cost you money by your pump running faster. Wow. Air pocket's going to cost you money by your pump running faster. Absolutely. You got air in that cooling coil, in that center coil. That means if you got air in a water cooling coil, it's not going to work too well. The heat transfer is not there. So nobody's happy because you're not getting cold air off the coil. You got flow through the coil on the bottom of the coil, but the whole top of your coil is full of air. So you got flow through the coil, but the top of the coil is full of air. It's not working right. So what happens? The thermostat in the room on the wall says, I'm not happy, and tells the two-way valve to do what? Open, wide open. Now you got a two-way valve wide open on that center cooling coil to try to put more water through it, but the air in the cooling coil doesn't let it work properly. But now you've got more flow. Now your pump's got to run faster to give you more flow, even though you're not getting any cooling out of it, and you wind up with an energy hog. So getting air out of a system is critical to making sure you got an efficiently running system. It's very hard for some people to see this connection, and I hope you understand with this slide how important it is to get air out of those coils and get it back where it belongs to make your systems run at the minimum energy levels we can get them to run. So how about air in solution? What do we know about air? The hotter the water, the less air it can hold. You know what a deaerator does for a living? You know, a deaerator for a living, basically you heat the water up to drive air off. So if you cool water down, you suck air in. So the hotter the water, the less air it can hold. The cooler the water, the more air it can hold. You kind of got to understand these basic things that you already know. The lower the pressure of the water, the lower the air pressure on the water, the less air it can hold. The more pressure we put on water, the more air you can drive into it. So these are kind of fundamental things about air you already know. If you take a glass of water out of the faucet that's been under pressure, and you kind of sit on your desk, let it just sit there and kind of warm up, you would normally see little bubbles forming around the water coming up to the top because you've taken the pressure off. When you take pressure off, the water had a bunch of air in it under pressure. You take the pressure off, air starts popping out. So these are the rules we want to understand. So you're taking pressure off of the water. Is that cold water? That water is 60 to 70 degrees, sits on your table, it warms up. So you're warming the water up, driving air off. you're taking the pressure off, driving the air off. So what does that mean to you? The lower the pressure and warmer the water, the more air you get out of solution. So I wonder where the best place would be for an air separator. Well, wait a minute. You're telling me hot water and low pressure. You got it. That would be where you want your air separators to be. So the lowest pressure possible with the hottest water. So in a chill water system, we would normally put it with the return chill water. Return chill water would be 55, 56 degrees, which is probably the hottest point in the system. That's where we want the air separator. We also would on the suction side of the pump. And most times, in this particular situation, primary, secondary, you've got that little green bridge in there, but we're on the suction side of the distribution pump, which is normally the high head pump. So the ideal location on a primary secondary system for the air separator would be, as shown here, hottest water, suction side of the primary pump. When possible, place the air separator in the warmest water. In this case, we got a boiler. Where's the hottest water? Obviously, the hottest water is coming off the boiler, so we would prefer to pump away from the boiler, away from the air separator, away from the expansion tank. That gives me the lowest pressure and the hottest water, and I got my best shot to get the air out of it on startup. I really do. That's very critical. You understand that. So when you have a system under pressure, when you pop the top, what happens? You lose pressure, air comes out, and you now have an open system. I think this, going back to this old Coke can, is a great way to illustrate to you the difference in an open and closed system. And what is our goal? Our goal is to always keep that closed system. We don't want an open system. So let's keep this in mind a little bit and have a little fun and understand some of this. And related to this would be the system pressurization. And when you take pressure off of water, air pops out. When you heat it up, air pops out. Now, what in the world could this have to do with the Thames Tunnel River? Thames River in London is where the first large tunnel was made under the ground. And they actually, in 1843, tunneled down underneath the Thames River, which at this time London is probably one of the most active seaports in the entire world. The British Empire was probably controlling the world. This is London, and they put underneath the river now, in 1843, they dug a tunnel. You could walk through, as you can see pictures of it here, trains could go through it under the river. When it was completed, they kind of considered it the eighth wonder of the world. Now, it was 75 feet below the water level of the river, the lowest water level of the river. This tunnel was 75 feet down below that, so the ships could pass back and forth above. And kind of keep that in mind with system pressurization. This is a little fun. So when they finished up the tunnel, all of London were just so excited about what they were calling the eighth wonder of the world, 1843. They put a big party in the tunnel, and they had champagne, and they had a great big party down there. And they were drinking champagne. They were 75 feet below the water of the river. The river's above this tunnel. They're in the tunnel down below the river. Atmospheric pressure is up. Not a whole lot, but a fair amount. You're down below enough that the pressure is higher. They all were drinking champagne, all having a great time. And when they walked out of the tunnel, came up to the surface and rose up 100 feet or so in the air to get back on street level, guess what happened? Very simple. They all got intoxicated because the bubbles started coming back out. The champagne was full of bubbles. When it came to the roof, when it came to the surface of the streets of London, all those gas bubbles started coming out. And when it came out, people got sick. Thought they had a problem. This is one of the first examples of understanding what happens with pressure on gas. Pressure driving air in solution, taking pressure off, air pops out. Kind of a trivial tidbit, but it's kind of interesting comment. So there are lots of bubbles, air bubbles in water that you can control by pressure. And it's another example of milky water would be water under pressure. And when you take it out of a faucet and you put it in a glass, it looks milky because it's got so much air coming out of solution because you took the pressure off. So what can we do with this? Little thing you've learned about adding pressure to drive air in and taking pressure off to take air out. Which side of a cooling coil or heating coil would you put a circuit setter? Which side? And I'll show two different possibilities. I got my circuit setter on the left-hand side on the outlet, and on the right-hand side is on the inlet. Now remember, the worst place in the world to get air would be in the cooling coil. You don't want air in that coil. So by putting it on the supply side, let's take a quick look. If we leave the circuit setter on the outlet side in this case, keeps air out of the coil, because air removables from the system is very simple. So if I back up real quick, I want a circuit setter on the outlet side to keep the pressure in my cooling coil as high as possible to drive as much air in as I can. Therefore, all drawings that I've seen, all ASHRAE drawings I've seen, show the balancing valves on the outlet side of the coils, not on the inlet side. If they're on the inlet side, then we're reducing the pressure by the pressure drop through the balancing device, which lowers the pressure in the coil, which means air is going to pop out in the coil. If we put it on the outlet side, we keep the pressure higher in the coil, we drive air in solution there, and we can make it work much better. Therefore, we preach, everybody shows in the drawings, balancing devices belong on the outlet side of a coil, not on the inlet side. Air removal from systems, and there's a couple little tidbits here you might want to look at. If you go back to ASHRAE and Gil Carson, 1981, this is a trivial little thing, but worth looking at. If you can keep velocity above 2 feet per second, you can entrain air to take a vertical piece of pipe and take air down with you. If you get the velocity below half a foot per second in a piece of pipe or in any place, the entrained air is just going to pop out. So if you're building an air separator and that's all you've got going is you want to keep it below half a foot per second. If you've got a coil above you and you're trying to bring air down, you want to size your pipe on above 2 feet per second to bring the air down with you. So take a little quick look at a system sizer based on pipe size. Scale 3 gives you that velocity. So when you start looking at some of these, you need to kind of be aware of those velocities if you're worried about moving air around in a system. So let's go back to the air-bound system we had earlier. Here again, the pump's off, and you see that we got air trapped in a coil. Now, we said if we could size that pipe on 2 feet per second, we could take that air and bring it down. But the next thing is we got to make sure we get flow through the coil to entrain the air and bring it down at 2 feet per second. So the pump is off, air is trapped in a terminal. You see with the air coil, the water coil is 3 feet above the pipe, 3 feet above the pipe, and we've got air, what, 1.5 feet of air and 1.5 feet of water. When we turn the pump on, the pump raises the water on TA, lowers the water on TB, but we don't have enough pump pressure to force water through the cooling coil. So what do we got to do? If we added a circuit set on the return side and made sure the pressure drop of the circuit setter was higher than the elevation of the coil above the main supply main, then we could force some circulation. That's all we've done. We put a circuit setter on that piece of pipe with a 5-foot drop. That means I got to have more pump head now to make it flow, yes. But that extra pump head would allow me to get the water that much higher to the coil, and I can purge the air out of the cooling coil. Now, if I size my downcomers on 2 feet per second, now I've got a way to actually vent a coil at a high point by making sure the pressure drop through my circuit setter on the return side is higher than the elevation of my coil above my main pipe, above my supply main. That's critical, making sure you got more pressure drop through the circuit setter than the elevation. And we make sure we size it on 2 feet per second. We can actually take the air out of the coil. We can purge it right out. Nice little trick for some of you senior engineers listening to this. You may never heard of this. It works. It works like a charm. You just got to spend a little bit of time sizing your pipe properly. And you may have to actually put a circuit setter in there and put a little extra pressure drop to make sure you get the water up that high. Cute little idea, I really think it makes some sense. So if we start looking at velocity reduction air separators, the inline air separators, we got to be down to 6 inches per second to make sure the air comes out. We got to slow the water down. If we go to a roll air trough type of device, we have tangential flow. So now we got centrifugal flow, centrifugal force, air being lighter than water, air comes to the middle. The water on the outside where the biggest force is, we're bringing the air right out of it. So it really does a wonderful job of taking air out of the water using centrifugal force. Here's a little picture of that where we ran some stuff in the lab, did some CAD analysis type approaches to it, and you see how they work. We get the high velocity around the edges there, we just wring the air right out. These things work. So when you specify air separators, make sure you're looking for centrifugal connections. They really make a huge difference. Tangential connections where you get centrifugal force working for you. Here's some charts on the efficiency, but again, with tangential connections, we can control the efficiency and get up to 90% of the air out on the first pass. Of the entrained air, we can get over 90% of it out on one pass when we size them properly. So here's a little comparison between the inline air separators that do not have centrifugal force. You've got to get the velocity down to 0.5 foot per second versus air separators with tangential connections, spinning that water, centrifugal force, they can be smaller. So you see the capacity difference. So the message is, in your specifications, you should always demand tangential connections to make your air separators work much better. If not, and if it's just an inline kind of a tank, that inline tank has to be physically bigger to get it down to 0.5 foot per second to get the same air separation capability that a roll air trough will give. So this example shows you a 30-inch tank being roll air trough. This is 2,000 gallons per minute, where if you look at a 42-inch tank required for the inline type. It's hugely critical, real simple thing to add to your spec, making sure all your air separators come with tangential connections. Just that simple. It's not a very hard thing. And you might call this a boiler's best friend. We're seeing more and more buffer tanks. Now, by nature, buffer tanks a huge amount of water, and guess what? Very low velocity. So they really do make a great place as an air separator because we got the water down below 6 inches per second. You can put an automatic air vent, 107A air vent on top of these things, and they do a nice job of separating air. And then not the expansion tank. You still got to have that bladder tank or an expansion tank somewhere, but they can take care of the air separation bit. And if you've got a huge buffer tank, chill water, hot water, and you're slowing the water down to below 6 inches or 0.5 foot per second, they work really well as an air separator. So here's a typical lock and wall buffer tank. You can even have tangential connections on them if you wanted to make it get more efficient. This is not an expansion tank. Don't make that error. Thank you. Have a great day.